In this video, we present a real-time method for precise 3D hand poses tracking using capacitive touchscreen and demonstrate how our method significantly improves the experience of remote whiteboard interactions. Touchscreens enable users to interact naturally with digital devices via stylus or hand fingers. They are widely used as virtual whiteboards in remote communications. However, speakers' hand gestures are not visible to audience, which reduces the efficiency of interaction and immersive experience of remote communication. A lot of methods have been proposed to address this issue, using an additional camera installed on top of the screen to capture hand poses and visualize on the screen. These methods require complex system setup, which limited the application scenarios. In this paper, we achieved accurate 3D hand pose tracking using the touchscreen only. No extra device is required. Now, we introduce our method. When hands come into contact with the touchscreen surface, a real-time capacitive image is generated, highlighting the areas being touched. Our method takes the latest capacitive image from the image sequence as input. The joint position estimator employs a deep learning-based method, incorporating temporal information to predict hand poses and outputs the current 3D joint positions of both hands. Following this, the constrained inverse kinematic solver reconstructs 3D hand poses based on the 3D hand joint positions and outputs the 3D hand mesh of current pose. For optimal performance in learning-based hand tracking on touchscreens, we capture high-precision hand pose data that is accurately aligned with the touchscreen. Our system captures hand images from different views with 9 RGB cameras and reconstructs hand skeletons using multi-view stereo techniques. The hand skeleton is aligned with the capacitive images captured by the touchscreen. In this way, we created a high-precision, touchscreen-based 3D hand pose dataset. Now, we show experimental results. Our method can handle situations where hands are located on the edge of the touchscreen. Our method can predict accurate results even when the contact area between hands and the touchscreen is small. Our method is robust to situations where hands are close to each other. We compare our method with the most related work, touch pose. In the case of fingers tapping the touchscreen, sometimes only one finger is on the touchscreen. The results of touch pose are inaccurate and unstable, while our method works well. Furthermore, our method allows both hands to touch the screen at the same time, whereas touch pose is limited to processing a single hand. We give two exemplary applications of our method. First, we developed a whiteboard prototype system. Our system can simultaneously estimate the gestures of both hands, enabling the speaker to perform operations directly through gestures. The speaker can perform actions such as zooming, shifting the canvas, and erasing using a fist. In this way, we offer a more convenient method for speakers to operate on the whiteboard. When the speaker draws on the touchscreen, the drawing content is displayed. The speaker's hand and pen are also visible. In this way, we enable the audience to observe the speaker's writing process, enhancing the overall visual experience. Second, we developed a lightboard application, which allows the speaker to draw contents on the screen while facing the audience. When the speaker draws with the stylus on the touchscreen, his eyes are also concentrated on the drawing point. This feature provides an engaging experience for the audience. Enhanced by our hand tracking method, the speaker can directly point to the screen with their fingers. Furthermore, our passive deformation effect simulates hand touching the screen. Thank you for watching. Have a nice day.